Hello everyone, today we will be looking at a very important data science application which is using LDA or Latent Dirichlet allocation in big data analytics. The basic focus of this session will be understanding how topic modeling and latent Dirichlet allocation can improve the e-commerce business such as search engine and online advertising systems. After completing this video, candidates will be comfortable in solving LDA problems on their own at industrial setting. Candidates are required to have foundation in machine learning to learn topic modeling applications in big data settings. Let's answer the question that why do we need topic modeling? As more information becomes available, it becomes more and more difficult to find and discover what we need. Currently, we type keywords into a search engine such as Google and find a set of related documents. We then look at these documents and possibly navigate to other documents. Let's imagine searching and exploring documents based on these themes that run through them. We might zoom in and zoom out to find specific or broader themes. We might look at how themes change through time, how they are connected to each other. We can also find the theme first and then examine the documents pertaining to that theme. All of these searching and finding operations about related documents is done using topics. So what is topic modeling? Topic modeling provides methods for automatically organizing, understanding, searching, and summarizing large electronic archives without any prior annotation or labeling. It discovers the hidden themes that pervade through the collection. It annotates those documents according to those themes and uses those annotations to organize, summarize, and search the texts. We have talked about topics for a while now, so let us understand what a topic essentially is. A topic is simply a set of similar words. For example, in this figure, there are four topics 1, 2, 3, and 4. If we look at topic number 3, we can see that it has a lot of similar words like disease, diseases, bacteria, and resistance. While topic number 1 also has a lot of similar words relating to human genome, genetics, and sequences. So essentially, if we have a document such as this, which is a science journal, we can expect a topic modeling algorithm like LDA to generate topics which are set of words out of this document. The topics which have been generated are three, and these are colored in blue, yellow, and pink. So the blue topics are genes, genomes, and genes, while the yellow topics are genes, genomes, and genes, while the blue ones are computer numbers, computational, and predictions. We use a generative model in LDA. It considers documents as mixtures of topics, and a topic is a probability distribution over words. We will understand this phrase probability distribution over words on the next slide. Technically, the generative model assumes the topics are generated first before the documents are. Okay, this is the previous science journal. Now, the topics generated are essentially a probability distribution. The topic number 1 is colored in yellow and it has words such as gene, DNA, genetics, and other sequences and other words. So topic number 1 will not be essentially a set of these words, but it will give the probability of occurrence of each of these words in this topic. So for example, It will give the probability of occurrence of gene in topic 1. It will give the probability of occurrence of DNA in topic 1, and it will give the probability of occurrence of genetic in topic number 1. So this essentially is a probability distribution of the words. Now, let us look at the central problem of LDA. LDA takes an input the documents themselves, while the topic structure, the topics, the per document topic distributions, and the per document per word topic assignment is a hidden structure. The central computational problem is to use the observed documents to infer the hidden topic structure, that is, reversing the generative process. This is the meaning of reversing the generative process. We have been given in input the documents itself, or in this example, a single document which is a science journal. There are other documents behind this which have not been shown. The input is a document and the output is expected to be a list of probability distribution of words, or you can say a list of topics, and the topic proportions and assignments. Let us first understand what is the difference between statistical inference and probabilistic generative process. What probabilistic generative process does is, let's imagine that we have 4 lists of topics above. Probabilistic generative process combines all of these topics one by one and generates documents out of them. It tries to find out some documents having the highest probability of existence using some combination of these topics. For example, if we have 2 topics, money, bank loan, and river, bank, stream, bank, river, both of these have bank in common. However, let's just not consider it for a moment. Since they have bank in common, we need to distinguish which bank are we referring to. So we use a superscript on bank to distinguish. If we use only the keywords from topic 1, then we will get some document 1 as follows. However, if we use only the keywords from topic 2, we will get something like document 3. However, if we use both of these topics, we will get something like document 2. Now, let us look at statistical inference. Statistical inference is quite different. We get the documents as input, but we don't know which topic or what topic distribution or what per word topic distribution is being used here. So as you can see, we have question marks all over the words. The generative process does not make any assumptions about the order of the words in the documents. Hence, it follows the bag of words assumption. The way the model is defined, there is no notion of mutual exclusivity that restricts words to be part of one topic only. That is, it also captures polysemy. For example, you can look at the word bank here, and although the bank is a word which comes in 2 different documents, it will be handled appropriately by LDA. This was an example of capturing polysemy, by the way. Okay, now let's look at the graphical notation of LDA. The graphical notation is very interesting to look at. All of these circles are random variables and the shaded ones are observed variables. This means that these are the topics. So these are the observed variables that we need to look at. However, why is basically a dependent variable. What this means is that all of these variables are dependent on y. We need to solve y if we need all of these variables to exist. We use y to get all of these variables. This is the complete model of LDA. As you can see, to get WDN, which is the observed word, we need beta k for all k, and we need ZDN. For ZDN, we need theta d, and for theta d, we need alpha, and for beta k, we need eta. So now, what is alpha and eta? Alpha and eta are Dirichlet parameters, and eta is a topic hyperparameter, which is also a Dirichlet hyperparameter. We will talk about Dirichlet hyperparameters and Dirichlet parameters alpha and eta in a later slide. Let's assume that we have used these to get the list of topics or the probability distribution. Okay, so what essentially eta does, it gives us beta k for all k topics. So let's say that we have k is equal to 3, so we have 3 topics, beta 1, beta 2, beta 3. So beta 1 will be a probability distribution, beta 2 will also be a probability distribution, and so on and so forth. Right. So now we have d number of documents with us, and in each document we have the per document topic proportion. What this means is that theta 1 will be the proportion of the topics in document 1, theta 2 will be the proportion of the topics in document 2, and so on and so forth. Now, when we look at a particular document, we can consider n number of words in the document. That is, let us assume that there are n number of distinct words in a particular document. So now, we have something called ZDN, which is dependent on theta d, which is a per word topic assignment. What this means is that once we have the topic proportions in a particular document, we can take for each word in the document, we can find out the topic corresponding to that word depending upon the probability distribution. We will look at this algorithm in much more detail. Now, after this, we have the topic and we have the probability distribution of the topics. So we know we can try to find out which word is this topic being corresponding to. So that is the observed word, that is our output. Let us look at this model again in much more detail. Okay, so we have a hyperparameter eta, and we use the Dirichlet of beta to find beta I for all 1 to k. So beta 1, beta 2, beta 3 till beta k are all probability distributions. So beta 1 is basically a probability distribution of topic number 1, beta 2 is a probability distribution of topic number 2, and all of these topics. So now what do? We look at each of these documents, and for each document we draw theta d using alpha, and theta d gives us the proportions of the topics in each word, in each document. So yes. After this, we take each and every word from that document one by one, and we draw ZDN out of a multinomial distribution of theta d. Let's say that ZDN comes out to be 5 or 4. So what this means is that the word that I chose is in topic number 4 according to theta d. According to theta d, it is in topic number 4. So now what do is we find out WDN. So how do we find out WDN? We look at topic number 4. We look at the probability distribution of topic number 4. The probability distribution of topic number 4 is beta 4. We'll come here at beta 4 and we look at beta 4. And beta 4 gives us the probabilities of different words in the topic. Using that, we predict WDN. So this is how the generative model of latent Dirichlet allocation works. However, we have not still understood what is the use of alpha and how it works. Alpha is a very interesting parameter and we will look at it in the next slide. The Dirichlet distribution is an exponential family distribution over the simplex, that is positive vectors that sum to 1. Let us look at the algorithm and try to understand what this means. The first step is draw each topic beta I from Dirichlet of n for I belonging to 1 to k. For the sake of simplicity, let us assume that k is equal to 3. So we have 3 topics, beta 1, beta 2, beta 3, right? So for each beta 1, let's say for beta 1, we need to find out the probability distribution beta 1. Then we need to find out the probability distribution beta 2 and also beta 3. So let us look at beta 1 for instance. Beta 1 constitutes of the probabilities of a lot of words in that topic. Let's say that there are p number of words. So the variables, let's say that there are 4 number of words, 4 words in each topic. So we have in topic 1 we have word W1, W2, W3, W4 and so on in each topic. So we need to find out assign probabilities to each one of them. How do we do that? That is where Dirichlet comes into play. What Dirichlet says is, okay, you give me all of these numbers, like tell me that what is the vocabulary set of words, and you give me the number of words that I need to assign probabilities to. For example, in this case, the number of words will be 3, right? So it tells us the probabilities of the different probabilities that we can assign to these 3 words. So let's say we had 3 different words, W1, W2, W3. All of their sum should be equal to 1. So W1 plus W2 plus W3 equal to 1. But their probabilities can be different. So it can be of the scenario where W1 is 0, W2 and W3 are 0.5, or W1 is 0.4 and W2 and W3 is 0.3 and 0.3. So which probability to use where? So Dirichlet of eta and Dirichlet of alpha gives us the probability of choosing a particular probability distribution. But this alpha can be very much affected by the magnitude. This probability distribution can be affected a huge amount by alpha's magnitude. When alpha is less than 1, there is a bias to pick topic distributions favoring just a few topics. For example, let us look at the effects of alpha. When alpha is equal to 1, you can see that we have picked these 15 probability distributions. So why do you think we would be requiring to pick 15 probability distributions? Because there might have been 15 different documents. For each document, there will be a theta 1, theta 2, theta 3. So theta d will be for 15 different probability distributions. As you can see, it is trying to favor the probability distributions which have slightly dominating personality of one or two or some finite small number of keywords. Let us look at alpha equal to 10. As I increase the number, it, it chooses the probability distributions having equal amount of probabilities throughout. As I increase it further, you can see that all of these are equal now, almost equal. Once I decrease it to 0.1, you can see how the values are shot up and changed. It is choosing the probability distribution in which all of the other items are zero, but this one is huge, so this is completely wrong. And if I choose it to be further down the line, it goes haywire. So all of these things are really important while designing an LDA algorithm. However, Python consists of latent Dirichlet allocation as its inbuilt library. So we'll be using that in our next problem on Kaggle million news headlines dataset. Thank you.